this vector, you'll see that you get the right thing. So using this representation, using the fact that there's factors, we can go and make a circuit that computes this. So the top is just from the previous page. Here we have the factored state again. Now we want to go through each bit and construct the circuit. Okay, so we'll start with the left bit. So the left bit just depends on A sub m, and that's going to be the bottom wire. And so to get this phase up here, we need a Hadamard transformation. And that's the whole bottom wire, what we need to affect it.
What does that mean, 0 point AC?
That means this is just binary. So this is A sub m over 2. So this is second root of unity to the A sub m power. And in general, it's the same thing. It's just a binary representation. So then we can do the next bit up. So we'll do this line. This line depends on the bottom two bits, A sub m minus 1 and A sub minus 2. And to get those two, you need a Hadamard and a controlled rotation. So a rotation puts in this root of unity to the right power. And then we can go up the line. Finally, at the top, we have this phase we need to put in that's dependent on everything. Let me put that in. And that's the circuit that computes the Fourier transform. And so if you remember from yesterday, the restriction we needed to say that a transform could be computed efficiently was that it was based on these gates that uses just 1 or 2 qubits, and that's what we have here. We're only using a Hadamard, which works on 1 bit, and we're using these rotations, which are controlled on 2 bits. Right? So these control gates say, put in this rotation if this bit down here is 1. So this is inefficient.
Shouldn't the rotation be diagonal?
Excuse me?
Zeros are the off-diagonal for the rotation matrix.
The rotation matrix. Oh, well, this is not the controlled rotation. This is just the rotation.
No, but the rotation should be diagonal.
Oh, I see. Yeah, you're right. It should be diagonal. Thank you. Yes. Okay. Any other questions? Okay. So that's how you compute the Fourier transform over a power of 2. Just using these 2 gates down here.
Well,
yeah.
I don't know this one. What does it mean by diagonal? If it is not right, so what is going to be right rotation?
This is a 0 and this is a 0.
Thanks.
Okay, so now I want to move on to computing the Fourier transform over any cyclic group. This was first done by Kataev, and then later there's a simpler algorithm I'm going to talk about today, and it's faster in some cases. And there are also parallel versions where if you want to have shallow quantum circuits, you can get those too. Okay, so before I tell you what the algorithm is for computing the Fourier transform over a cyclic group, I want to tell you 2 facts, and these are 2 of the components used in the algorithm. I just want to talk about them individually first. So the first thing is, okay, so what we need to do, right, we're going to manipulate the superposition using simple manipulations in order to get the Fourier transform. So the first manipulation we want to look at is what happens when you repeat the vector. So this top left corner is my picture for arbitrary superposition. And this is a made-up Fourier transform of it. So we want to look and see what happens when you repeat the vector s times and compute the Fourier transform over the larger group. So here it's of size Sn instead of size n. And what happens here is it's just a simple calculation. You just get the same superposition as up here, but spaced out. So you still have the same n points as up here. They're just evenly spaced every s. Okay. The second fact is what happens when we do 0 filling. So here, we're going to start with our superposition and embed it in a larger space. So here we're not repeating it. It's just all zeros. We just choose Q to be really big. We compute the Fourier transform over the larger group, and then we get something that looks more messy than before. It's not as nice. We can still pick out these values of the Fourier transform over the smaller one by picking evenly spaced points. But these red points are a problem, and we have to throw them out if we want to have close distributions. So this throwing out of red points is wasteful, and it's a problem. But in the Fourier transform algorithm, we combine these two facts, and by spacing it out and doing the zero filling, these red points become useful. And we don't have to throw them out anymore. And that's actually how the Fourier transform algorithm works. So here's how you do the Fourier transform over a cyclic group. So the top line is what we're after up here. We want to compute the Fourier transform of an arbitrary superposition. And the way the algorithm works is down the left-hand side. So we start off by repeating s times. So now we have the superposition repeated. These are just simple manipulations. Then we zero fill out to a large power of 2. This is, you don't do anything. You just consider it in a larger space. Then you compute the Fourier transform over this large power of 2. This is where we use the power of 2 as a subroutine. And then there's a particular measurement you can do that picks out evenly spaced points. And it doesn't have to be these evenly spaced points. So it can be offset by any amount also. But this is just one example of what the measurement might result in. And once you get these, then it's just a matter of scaling it down, re-indexing, and you'll get the desired superposition. So
what's the role of the repetition? Why cannot use it applied right away?
you can't use just the zero filling because of those red points. They interfere with each other. So neighboring points, they kind of spill over and they'll spill into each other. But when you separate it first, when you do the repetition, it separates them a lot. And then when you take the zero filling really high, it takes lots of samples from that little spike. And that gives you a really good approximation.
Why don't we just simply repeat it until up to however to not, instead of filling zero, we repeat, keep repeating.
Well, the problem is n might be a prime. So even if s is a power of 2, n won't be, like s times n won't be a power of 2. Is that what you're asking?
Yeah, for the step zero filling.
Uh-huh.
Instead of with filling zero, we do in the repeated of that.
Oh, why not repeat it?
Why not repeat it?
That might work with different parameters. I don't remember offhand whether or not that's okay. The question was whether or not you can just repeat this instead of zero filling. The zero filling does serve a purpose because what happens is when you zero, there's a fixed underlying continuous curve that these samples are coming from. And as you zero fill, it takes more and more samples from that. And in the end, actually, it might be necessary to zero fill because in the end, you have to take lots of samples because of this measurement down here.
Repeat it out all the way. You get a direct distribution, but you don't get the right superposition.
You get the right okay. You can use it to sample. If you only care about the magnitudes, that's okay, but the phases will be wrong.
Can you explain a little bit what you mean by sampling? There was no sampling in the previous slide.
Oh, I didn't say what sampling is, right? Thank you. Okay. If you were to, when you measure a quantum state, you get an induced distribution over the index on this vector, right? So this would give you a probability distribution over all these. That's what we mean by sampling. So in that case, you're not worried about what the complex number it is. You're only worried about its magnitude. So it's sort of I'll talk about that next. But. Any other questions on that? So here are some parameters. So this is right. We have this algorithm. I put it FP up here. I mean FN. Okay, I guess this is if you're doing it over a prime, but it doesn't matter. P can be any integer. If you want to approximate the Fourier transform over any integer, then the parameters are like this. You repeat the vector log squared p over epsilon to the 4th times, and then you zero fill out to s times p over epsilon squared. And this epsilon, so the theorem is that you get an epsilon approximation to the Fourier transform in the running time. In this case is n log n plus this other term. So in hindsight, this algorithm maybe isn't that hard, but there's still one non-trivial thing is we got the bounds pretty tight. So getting this log squared p was tough. getting it to just be a P isn't so hard. Okay, so in this algorithm, yes?
So where is the zero fill in that?
That's, it goes,
It's repeating, and then where's the...
Q represents how far we zero filled.
Oh,
Right, so we repeat it out to S times N and then up to Q, zero fills. Okay, so the second thing was, N is log. P is N here. That's just, no, it's not. Oh, yeah. No, okay. Sorry. I changed my notation somewhere along the way. Yes, this N down here is, what, log P? I mean, we want it to be polynomial in log P, and that's what it is. Yes?
Can you compare that if epsilon is rather small,
Yes.
then Q will be many times greater than SP?
If
I was under the impression that Q had to be quite close to SP.
no, Q can be way larger than SP.
Won't that make the final distribution look much more like the zero transform rather than the transform you're after?
What do you mean by the zero transform?
You're putting very little information in if Q is a lot bigger than SP.
Little information. So you're saying that if Q, okay, so I think the question is if Q is shooting way out here, then the support is small, and so there's little information. Yeah, it's true, but it helps because it tightens up this thing where you're sampling from the continuous curve. This measurement on the bottom is gonna pick out what you need in the end.
But are you not going to need to do exponentially many measurements in order to refine out that small support? If
No.
the is exponentially small?
No, you don't. It's okay. This measurement on the bottom will pick out one that works. Yeah.
Another question. So the speed is not faster than FFT.
It is.
As far as the angles.
It is. I just wrote it down wrong. N is log P. So it's the one I showed you. If you can ignore this line or just replace N with log P, then it is. It's exponentially faster. Sorry for the confusion. Okay, so the other thing is we use this Fourier transform over a power of 2 as a subroutine, and we can pick whichever one we like. So here are two natural choices. One's the Coppersmith approximate circuit. This uses the circuit that we saw before, but throws out small rotation gates to just get an approximate version. And that's what, well, okay. If I wrote this bound right, that's what this bound would be based on. And another option is the parallel circuits. One of the things they do there is they have a parallel circuit over a power of 2, and if you can plug that into ours and change a few things and get parallel circuits here too. Okay, so that's everything about computing the Fourier transform. Are there any more questions on that? Okay, so now I want to talk about Fourier sampling and the hidden subgroup problem. So first let me tell you about the hidden subgroup problem. This is the main problem we know how to solve in quantum algorithms. So the problem is you're given a function defined on a group that's constant and distinct on cosets of some unknown subgroup, and you want to figure out what that subgroup is. So here's a picture with a group with elements. Here's an unknown subgroup. And if you evaluate the function, in this case, you get these colors. So you have the subgroup, and you have translates of the subgroup of the cosets. And you evaluate the function on a coset, you get the same color, different cosets, different colors. And I'm not going to tell you exactly how the reduction works, but here are two examples factoring in discrete log. So for factoring, the group would be Z sub m, where m is Euler's phi function of n. So here there's already a hitch because you don't know what the group is, but I'll talk a little bit more about that in a minute. And another example is discrete log over a prime size field. You're working over Zp minus 1 cross Zp minus 1. Okay, so the algorithm for solving this is going to use the Fourier transform. That's why we're talking about it. And before I tell you how that works, let me tell you two properties about the Fourier transform that make the algorithm easy to analyze and see how it works. So the first property is if you have a superposition that's concentrated on a subgroup of a group, that's this right here, this sum is over elements in a subgroup, and you compute the Fourier transform, you end up with a state that's concentrated on something called the perp group. So this is another subgroup of a different group. The second property is convolution pointwise multiplication property of the Fourier transform. So here I've just written down an example. Here I have a delta function g. So this notation, remember, means it's just a delta function. So it's just a vector that is just concentrated at the element g, convolved with this state, which is a subgroup state that we saw up here. Right? And remember, this property says if you want to compute the Fourier transform of the convolution of two vectors, you can compute the Fourier transform of each vector individually first and then do pointwise multiplication of the two vectors. So in this case, the Fourier transform of this you get by computing the Fourier transform of a delta function, which is uniform over everything, and the Fourier transform of the subgroup, as we saw up here, over this perp group. I should say, I guess I didn't say that there are no normalization factors in this talk. So vectors are always norm 1 vectors when we're talking about quantum states, but I'm leaving out all the normalization factors. Okay, and then pointwise multiplication we have here, you get this. So the support is on this H perp just like before, and you have these phases sitting in there. So these are the two properties that will be used. Okay, so the first step of the algorithm for solving the hidden subgroup problem is to first create a state that is concentrated on a coset. So remember, we're given this function that's constant distinct on cosets. And what we do is we start here on the left with two registers initialized to 0. We compute the Fourier transform in the first register, which gives a uniform superposition over the group elements. We evaluate the function into the second register, and that gives us this state over here. Right, so this state is a superposition over all group elements together with the function evaluated at the group element. Okay, so the next step then is to measure the second register. This is just a step that helps us think about it. You don't actually need to perform the measurement, but if we perform the measurement, remember, we'll see this color. We'll see one of those colors. And remember, when you measure part of a superposition, the superposition will collapse to everything that's consistent with that. So in this case, when we see a color, it's going to collapse to a coset. So after you measure, here we have the color we measured, and now what's changed is the sum. The sum is over just the subgroup instead of the whole group, and the elements are over the coset, where G is the coset representative. So each time we perform this operation, we get a different coset representative that's uniformly distributed, because that's based on what the function value is that we see. And since we never use this second register that we measured again, we just rewrite it like this. So this is a quantum state that's concentrated just on a coset of the subgroup. Okay, so the next step of the algorithm after we generate this state that's on a coset, so here we have our state that's just on this one coset, is we Fourier sample. So we compute the Fourier transform and we measure the result. And what happens is when we measure the result, we'll measure from a distribution that's just concentrated uniformly over H perp. And the reason that this works like this is because of these properties of the Fourier transform. This coset state can be written as a convolution of a delta function together with the subgroup state. And then we saw what happens with that. We get a superposition that's concentrated on H perp that has the coset representative hidden in the phase there. So it doesn't affect the distribution that we see when we measure. So this gives us a procedure. If we repeat these first two steps of creating a coset state, then Fourier sampling, each time we do this, we measure a random element from H perp. And since H perp is a group, we can take polynomially many samples and have a set of generators for it. So that'll be, so the last step is to classically reconstruct H from these samples for H perp. Okay, so that's how the algorithm works. Yeah.
So for the classical approach, H would just be the set of all group elements where F takes the same value as the identity.
Where F takes,
For the classical approach, H would be the set of all group elements where F takes the same value as F, as it does at the identity.
at the identity, that's right.
Yeah, now where does that break down? I mean, you're evaluating F
Mhm.
a lot to take these Fourier transforms,
Where does that,
break down in the quantum approach. Where does the classical approach, which seems simpler intuitively, break
well, the group has exponential size, so you can't actually query the function and find collisions like that. Right, so the question is, you're looking for, to know that you have the subgroup, you want to, if you evaluate F at the identity, then you want to evaluate F at other group elements that evaluate to the same element, since it's constant on the subgroup. But the problem is the group has exponential size, right? You want to solve this problem in time that's log the size of the group. So you can't just query the function in lots of places because it'll take too long.
Don't you have to query the function everywhere to take the Fourier transform?
You do, but the model here is you evaluate the function in superposition. And when you evaluate the function in superposition, that takes one step. So back here, right? So here, we're in a superposition of all group elements. And then we query the function into the second register, but that takes one query, and it does all of them at once. Yeah.
You assume F that you apply in the second step is unitary, or you have to create
Sorry, what's it?
the F that you apply after you apply Fourier transform.
Yes.
It's supposed to be unitary transformation, right?
Yes.
So you assume that is a unitary transformation.
Well, okay, so the question is that this function f should be a unitary transformation. So I just didn't tell you something. There's a way you can define this so that it makes sense is you can take the function value f and you can exclusive OR it into the bits of the second register. So this 0 could have been anything. It could have been any bit string, and then you would have the function value here exclusive ORed with the bit string, right? So then if you do it again, you get back the original bit string, so it's unitary. Does that make sense?
If I understand, after the measuring that function results when the state collapsed to one color, in the second register we've got also collapsed state by and remains only those samples who result in this color.
Okay, say that again?
Okay, after measuring the function results,
Uh-huh.
yes, we've got the function results register collapsed into one of the colors.
Right, so the second register is
And
fixed.
the second register also collapsed.
The first register,
Yes, in all the samples that result in this color.
yeah, all the group elements that result in that color. That's right. Did you?
I think maybe, well, you might have added the measurement in your next slide.
Yeah.
It's like measure a random element of H.
Yeah.
Is it the result of the, isn't it the result of the measurement? I'm not quite sure.
Yeah, that's what I mean.
I mean,
That's what I mean. You measure the state,
you measure the state.
and yes,
Yeah.
that's what I mean. You get a sample from that's a random element of H perp. H perp, you do it in the abelian case. It's just with group characters. It's the set of characters that map the subgroup to the identity. Okay. Anything else?
So H perp is not in G.
H perp is not in G, not in general. Yeah, and Leonard will talk about what happens in the non-abelian case where it's more complicated. You have the Fourier transform uses representation theory and matrix entries. But things are a little simpler in the abelian case, so I'm kind of sweeping that under the rug for now. Okay, so that's what happens with the hidden subgroup problem. What I want to talk about next is a case where it always doesn't it doesn't always work out this nice. So in this case, we had a finite group, and we could compute the Fourier transform over a finite group, and we had these nice group properties. But there are cases when this doesn't happen. And so I want to talk more generally about Fourier sampling. So let me just say again, Fourier sampling is computing the Fourier transform and measuring. And so we start with an arbitrary superposition, we compute the Fourier transform, measure the result. And what happens here, what we're interested here is the distribution that's induced by measuring the resulting state. So we don't care anymore about what the actual Fourier transform is, what the phases are and everything. We only care about the distribution induced. And we want to see what kind of manipulations we can do to get this same distribution. And the motivation for this is, the structure of many quantum algorithms is like we just saw, where you repeat this thing where you set up a state, you Fourier sample, you repeat this many times, sampling from a probability distribution, and then you classically reconstruct the result. So here's an example of where things don't work out so nice. And this is finding the period of a periodic function. So factoring reduces to this problem, so that's why I'm talking about it. And I'm not going to tell you what the reduction is, but John will in his talk. So the setup looks similar. You're given a function that's periodic. So the difference now is that it's defined on the integers, and the integer is not a finite group. And when we say it's periodic, we mean like before. The subgroup, it's constant distinct on cosets of a subgroup, and that subgroup represents the periodicity. So if we try and solve this problem using the properties we just saw for the hidden subgroup problem, you can sort of think about it in two cases. So there's a clean case where everything behaves just like before. We can set up a superposition over a subgroup. In this case, it's periodic with period r. And if we know a multiple of the period, so we can actually, so suppose in this case n is a multiple of the period, a multiple of r, then if we were to compute the Fourier transform, we'd be concentrated exactly on, this is h perp, this is just another periodic superposition. And if we could sample from this right-hand side, we could go back and compute what the period r was. The problem is we don't know a multiple of the period, right? We're just given a periodic function. But we still have to set up a superposition somehow. But it's impossible to set up this one. So what's actually done, and this is one of the things Peter Shor had to do in his paper on factoring, is he handled this case of what happens when it doesn't line up right. So the solution is you pick some other boundary q, and you repeat the periodic superposition up to q. You compute the Fourier transform over that larger group, and you see what happens. And so things aren't as nice here. But that's something that Peter Shor showed you can still do after some classical post-processing. And so the main theorem we want to talk about now for Fourier sampling is we want to talk about reducing the useful case to the clean case. So the purpose of the theorem we're going to talk about is any time you can't set up your superposition or you can't compute the Fourier transform or whatever to use these exact nice group theoretic properties. But if there is a related clean case underlying, like there is in this case there's an underlying clean case that we can't use, you can use this theorem without having to reprove everything. Okay, so I'm just going to try and give you an idea how you apply it, the theorem. And the setup is like this. Okay, I guess I've changed my notation for arbitrary superposition. Now this is arbitrary superposition. And even though this is continuous, it's still discrete and everything. It's a discrete superposition. So suppose you're given an arbitrary superposition, or suppose there is an arbitrary superposition. You don't actually have it. And you don't know what its length is. You don't know what n is. Then the theorem, okay, remember we're talking about Fourier sampling. So what we're interested in is this distribution d over here. If we were to compute the Fourier transform of this and measure, we want to find other ways to approximate d without actually having n. So the theorem says that we can get an approximation to d called d prime by doing the following manipulation. So this manipulation, this looks like how the Fourier transform algorithm works. And actually the Fourier transform algorithm came from this. So the way it works is if you take your arbitrary superposition, if you have access to a repeated copy of it, so you can repeat it out an arbitrary amount, you compute the Fourier transform over a larger group. Then what you do is you take a sample from this distribution on the right-hand side, and you compute the continued fraction expansion of the sample divided by q. Okay, so the continued fraction expansion is going to give you a rational number, I over n. So remember, we don't know n, but by following this procedure, it'll give you a rational number, I over n, in any case. And that gives you two closed distributions, d with d prime. Now, there's a hitch here in that d prime is a distribution over integers. So say you might sample up here and see some integer I. If you repeated the process down here, you'd get I over n. And I over n is in reduced terms. So if I and n are not relatively prime, you actually have less information. But in any case, these distributions can be made as close as you want by adjusting the parameters. And this gives a general way where, see, we didn't know n or anything. All we had access to was this repeated superposition, and it was easy to analyze. It was easy to get a distribution approximating d. Okay, so I'll show you how to apply this to Shor's algorithm. If we wanted to apply it here. So remember, the setup is we have this superposition here with n that we don't know. We want to figure out what n is. So for Shor's algorithm, what you plug in for alpha is just the vector that is 0. Just this superposition right here, just the smallest unrepeated part. And we know that if you take just this delta function 0 and compute the Fourier transform, that you get a uniform distribution on the right-hand side. So that means if we go through this other process I talked about of repeating it out, computing the Fourier transform over the larger one, and computing the continued fraction expansion of the result, you'll get a fraction I over n where I is uniformly distributed between 0 and n. So the two distributions we're comparing, on the top we got d, which is an integer between 0 and n minus 1. And on the bottom we got a fraction, I over n, where I had the same range, 0 to n minus 1. Any questions?
It seems like if you don't know n, there'll be situations where repeating this superposition is not so easy to do.
Yeah, the situations we're talking about, you have access to repeated superpositions.
Without knowing.
Without knowing n. So here's another example. This is just an example of somewhere this comes up. You have the Lasagna symbol. So the Lasagna symbol is a function that tells you whether or not an element in a prime-size field is a square. It takes values plus and minus 1. And so we could say, okay, suppose we can evaluate this symbol, but we don't know what the size of the field is. So it's a black box function that gives us plus and minus 1. And this thing is also defined beyond p, right? Because you can just reduce the input mod p and get the same value. So what we could do is we could set up a superposition and put the Lasagna symbol in the phase. And so we'd get this repeated superposition that just takes values plus and minus 1. And we'd like to analyze this and see what happens. So using the theorem, we can go back and look at the smallest unrepeated part. And so here, what happens is the Lasagna symbol is an eigenvector of the Fourier transform. So if you compute the Fourier transform, you get the same vector. And since we're only interested in the distribution turns out to be uniform, because all the values it took were plus and minus 1. So that means that if we do this experiment down below, where we have this repeated version, we're going to get fractions I over p. Right? So using this procedure, you could figure out what the period was. Okay, so I was just telling you about the Fourier sampling theorem. It's useful when it's not possible to use this nice clean group theoretic setup that exists in the hidden subgroup problem. And it also showed that Fourier sampling, right, when you're only worried about the distribution induced but not the actual complex numbers, that Fourier sampling, it's robust under group changes. So we had these manipulations where you could use Fourier transforms over different size cyclic groups and still approximate the distribution you wanted. And this can also be useful for other cases. Say, if you just want your algorithm to run more efficiently, you could, by using the Fourier transform over a power of 2, even though you wanted some other modulus. You could use this to just get a nice approximation. And there are other applications, other examples. For example, functions that are not distinct on the cosets, right? So remember in the hidden subgroup problem, one of the conditions, the function was constant on each coset, but on different cosets it was distinct. And here you can relax the condition so that many cosets all go to the same value. So you don't have this nice coset state anymore. You have a superposition of lots of cosets. And earlier it talked about how to compute the Fourier transform over finite abelian groups and the hidden subgroup problem. And that's it.